On the morning of March 14th, 2026, a team of geophysicists published a paper in the journal Science Advances. It did not make the front page. It did not trend on social media. Most people never heard about it. But inside that paper was a single sentence, a single clinical, carefully worded sentence that caused several of the researchers who read it to stop, to reread it, and then to sit very quietly for a moment. That sentence described something they had found inside the Juan de Fuca plate, the ancient slab of oceanic crust that has been slowly, silently diving beneath North America for 10 million years. They found a tear, a structural split running through the interior of the plate itself, cutting across a section of the Cascadia Subduction Zone that had previously been mapped as the most locked, the most stable, the most dangerous segment of the entire fault. Because to understand what it means, to truly understand what this discovery tells us about where we are right now, you first need to understand the thing that has been sitting beneath the Pacific Northwest coast for the last 326 years, waiting, not moving, not releasing, just waiting. There is a wall offshore. You cannot see it. You cannot feel it. Not today, not this morning when you woke up. But it is there, running 1,000 kilometers along the floor of the Pacific Ocean, stretching from the coast of Northern California northward through Oregon, Washington, and all the way up the coastline of British Columbia. That wall is the boundary between two tectonic plates. On the western side, moving steadily eastward at roughly 4 centimeters every single year, is the Juan de Fuca plate, a dense, heavy, ancient slab of oceanic crust, cold and dark and massive, pushing eastward without pause, without rest, without mercy. On the eastern side, the North American plate. Everything from the Rocky Mountains to the coast, Seattle, Portland, Vancouver, every building, every bridge, every road and school and hospital sitting on a continent that is being slowly, incrementally compressed, 4 centimeters per year. That sounds like nothing. It is almost nothing, until you multiply it by 326 years. That calculation produces 1 meter and 30 centimeters of displacement, 1 meter and 30 centimeters of tectonic movement, all of it absorbed entirely as strain, stored, locked inside the boundary between two plates that cannot slide past each other, that are fused together by friction across a zone hundreds of kilometers wide and tens of kilometers deep. That energy has nowhere to go. It does not dissipate. It does not bleed off slowly in small, manageable earthquakes. The locked zone does not allow that. The locked zone is a closed vault, and everything going in stays in, every centimeter, every year, every decade of silence. It is all in there, right now. Here is the thing that most people have completely backwards. When you look at a seismic activity map, your instinct is to fear the regions with the most dots, the areas showing frequent small earthquakes, the active zones, the places that shake regularly. Your instinct is wrong. The most dangerous seismic fault in North America is not the place on the map where earthquakes are happening. It is the place where they are not. The Cascadia Subduction Zone offshore, the locked interface where the plates are fused together, shows almost no seismic activity. In decades of instrumental records, the offshore section of the fault has been nearly silent. No moderate earthquakes, no releasing tremors on the main fault surface, nothing you would report on a news broadcast, nothing that would interrupt your evening. In seismology, this pattern has a name. It is called a seismic gap. And the scientific community has learned, sometimes through catastrophe, what seismic gaps actually mean. They do not mean safety. They do not mean the threat has passed. They mean the lock is holding. They mean the energy is not escaping. They mean everything, every joule of stored elastic strain from 3 centuries of convergence is being conserved for one single moment of release. Think of a rubber band stretched between your hands. Pull it gently, it holds. Pull it harder, still holds. Keep going. The rubber band is not breaking, but with every millimeter of additional stretch, it is storing energy proportional to that stretch. When it finally snaps, every joule of that stored energy releases at once, in an instant, in a crack that you feel in your fingers and hear across the room. Now imagine that rubber band is 1,000 kilometers long. Imagine it has been stretching continuously for 326 years. Imagine the last time it snapped, the shockwave crossed an entire ocean and was recorded by officials in Japan who had no idea what had caused it. That is Cascadia, not a metaphor invented to frighten you. Not a dramatic simplification for a general audience. That is the physical reality of the fault system, sitting 80 kilometers off the coast of Portland, Oregon, right now, beneath 2,000 meters of cold Pacific water, in the dark, accumulating strain, waiting for the friction that holds it together to finally, inevitably fail. Let me give you another way to understand the scale of what is stored. The total elastic strain energy accumulated in the Cascadia locked zone over 326 years is not a number that has a comfortable everyday equivalent. Scientists measure it in terms of the moment magnitude scale, the same logarithmic scale that places a magnitude 9 earthquake at roughly 32 times the energy of a magnitude 8 and 1,000 times the energy of a magnitude 7. A magnitude 9 event releases energy equivalent to approximately 25,000 nuclear bombs of the Hiroshima design. Not in a controlled sequence, not distributed over time, in minutes. That energy is what is currently locked in the fault system beneath the Pacific Northwest coast. It has been accumulating since 1700. It has nowhere to release gradually. The physics of the locked zone ensure that when it releases as a rupture, as the sudden catastrophic failure of the friction interface that has held these two plates together for 3 centuries. The question has never been whether that energy exists. The question has only ever been when the friction fails. The Oregon Department of Emergency Management, in its official public-facing documents, government documents, accessible right now on their website, states that scientists currently estimate there is a 37% chance of a major Cascadia rupture of magnitude 7.1 or greater within the next 50 years. 37%. Consider what that probability means in the context of your daily decisions. A 37% chance of rain and you carry an umbrella. A 37% chance of a traffic delay and you leave early. A 37% chance that the fault 80 kilometers offshore produces an earthquake that shakes the Pacific Northwest for minutes, not seconds, minutes, and then sends a tsunami toward a coastline where some communities have 13 minutes to evacuate. That number is not the estimate of a fringe scientist writing on the internet. That is a state government's official estimate of its own risk, written down, published, available to read. And the British Columbia government published its own version in late 2025 in their Disaster and Climate Risk and Resilience Assessment, produced through the Climate Ready BC programme. Provincial officials explicitly modelled a magnitude 9 megathrust Cascadia earthquake as one of the most significant catastrophic scenarios the province could face. They cited research placing the probability of a full zone magnitude 9 rupture at between 2 and 10% within the next 30 years, 2 to 10% in 30 years for a magnitude 9 earthquake. The kind of earthquake that killed 230,000 people when the same category of fault ruptured in the Indian Ocean in 2004. Let that number sit for a moment. 2 to 10% in 30 years. That is not a negligible risk. That is the kind of risk that drives billion-dollar infrastructure decisions. That is the kind of risk that changes how buildings are designed and bridges are engineered and hospitals are located. That is the kind of risk that a functioning society plans around. The question we are going to spend this entire documentary examining is, are we planning around it? There are trees on the Washington coast that have been dead since 1700. They stand exactly where they grew, in coastal marshes, preserved in the cold and the salt and the anaerobic mud, grey and silver and perfectly still. They have been dead for 326 years. They died on a single night. They did not fall. They simply stopped living, killed in place by a sudden inundation of salt water that swept inland without warning on the evening of January 26, 1700. And they are among the most important pieces of geological evidence in North America, because they are the signature of the last time Cascadia spoke, the last time the rubber band snapped, the last time the vault opened. We are going to examine that night in detail in the next chapter. Because what happened on January 26, 1700, and more importantly, how scientists came to know precisely what happened, is one of the most extraordinary forensic achievements in the history of Earth science. But before we get there, I need to leave you with one thing, one number, not 37%, not magnitude 9, not 326, 13 minutes. That is the estimated time between the moment a full Cascadia rupture begins offshore and the moment the leading edge of the resulting tsunami reaches the nearest coastal communities on Vancouver Island, not hours, not the 40 minutes that distant Japanese coastal villages had in 1700 when they saw the ocean recede before the orphan tsunami arrived, 13 minutes. Some communities will have less, and many of the roads those communities depend on for evacuation will already be damaged or destroyed by the minutes of violent ground motion that will precede the wave. This is not speculation. This is not a worst-case scenario invented to generate fear. This is what the modelled scenario in the British Columbia provincial government's own risk assessment describes as the sequence of events following a magnitude 9 Cascadia rupture. Their words, their model, their document. In the next chapter, we go back to 1700, to the night this fault last spoke, to the ghost forests and the orphan tsunami and the indigenous oral histories that preserve the memory of a catastrophe that European settlers never recorded because they were not yet here. And when you understand what happened that night, you will understand something else. Why the silence since then is not a reassurance, it is the problem. ACT2, the night the Pacific screamed. On the evening of January 26, 1700, there were no seismographs anywhere in the world. There were no GPS satellites measuring millimeter-scale ground deformation. There were no ocean buoys recording anomalous wave heights in the deep Pacific. There were no government emergency management agencies waiting to issue warnings. There was no warning system at all. There was only the earth and the sea and the people who lived beside them. And then, at some point in the evening hours of that winter night, the Cascadia Subduction Zone released approximately 3 centuries of accumulated strain in a single rupture. The break extended for roughly 1,000 kilometers along the fault interface. The magnitude has been estimated at approximately 9, possibly slightly larger. The duration of the rupture, the length of time the ground shook, was measured not in seconds but in minutes. Several minutes of continuous ground motion, the entire Pacific Northwest coastline dropped. In some areas, the land subsided by a meter or more in a matter of seconds as the upper plate, which had been bent downward by the locked fault for centuries, suddenly released and lurched seaward. Coastal marshes that had been above the tide line were submerged. Cedar trees rooted in those marshes were flooded with salt water and killed in place. Their roots, locked in the sudden subsidence, preserved by the cold and the anaerobic mud, they became the ghost forests that Brian Atwater of the United States Geological Survey would find and study. Nearly 3 centuries later, in the 1980s, the seafloor beneath the Pacific rose by several meters along the length of the rupture zone. When the floor moves, the column of water above it moves. That displacement propagated outward from the rupture in all directions as a tsunami. On the American and Canadian coast, the wave arrived within minutes. Low-lying areas were inundated. Villages on tidal flats were swept away. The oral traditions of the Maka, the Quilotu, the Hoa, the Quinault, and other coastal nations along the Washington, Oregon, and British Columbia shoreline preserved detailed accounts of that night. Accounts of the ground rolling beneath their feet like the back of a living animal. Accounts of houses collapsing as the shaking went on and on. Accounts of the ocean withdrawing and then returning as a wall of water that destroyed everything in the low areas along the shore. These accounts were not written down in the European tradition. They were carried forward through oral history, through ceremony, through the deliberate and meticulous transmission of knowledge across generations. For decades, scientists did not fully incorporate this testimony into their understanding of Cascadia's hazard. That was a mistake. When they finally did, the oral histories aligned precisely with every other line of physical evidence. The oral record of the 1700 earthquake is not a single story from a single nation. It is a convergence of independent accounts from coastal peoples who had no contact with each other in the European sense, whose languages were different, whose territories were separated by hundreds of miles of coastline, and who yet preserved strikingly consistent descriptions of the same sequence of events. The Hujath First Nation of Vancouver Island preserved oral accounts of a night when the ground moved violently and the sea came inland, destroying low-lying settlements and killing people who could not reach higher ground in time. The Maka Nation of the Olympic Peninsula maintained traditions describing a sudden collapse of land and an inundation that swept across their coastal villages. The Quileutian, people whose territory sits directly above the most strongly locked segment of the fault, had legends describing the earth as a living thing capable of violent, sudden motion, legends that researchers, when they finally listened, recognized as systematic preservation of disaster memory. Indigenous scholars have noted that these oral traditions are not vague mythology. They contain specific geographic references, specific descriptions of the physical phenomena, and in some cases, specific guidance encoded in story and ceremony about where to go when the ground begins to move. They are, in effect, a parallel early warning system developed over thousands of years of living beside one of the most dangerous fault systems on the planet. The formal scientific acknowledgement of this knowledge came slowly. But by the time the full Cascadia picture was assembled in the 1990s, the indigenous oral record was treated not as supporting evidence for the scientific findings, but as an equal line of independent evidence, one that, in some cases, contained information that the sediment record alone could not have provided. But the truly extraordinary part of the 1700 story did not come from the Pacific Northwest at all. It came from Japan, 8,000 kilometers away on the eastern coast of Honshu. Japanese officials and coastal villagers recorded something unexpected on January 27, 1700, in local time. A series of anomalous waves struck fishing communities in the provinces of Iwate, Miyagi, and Ibaraki. The waves damaged coastal structures, flooded low areas, and caused losses to fishing boats and shore installations. What made these waves strange enough to be carefully documented and preserved in provincial government archives for the next 300 years, was that there had been no local earthquake. In Japan, tsunamis arrive after earthquakes. The shaking comes first, and the people who survive know to move to high ground. But on January 27, 1700, there was no shaking before the waves. They wrote it down as a kind of anomaly. A tsunami without a parent earthquake, an orphan wave, that phrase, the orphan tsunami. It was those Japanese records that ultimately cracked the case open. Kenji Satake of the Geological Survey of Japan was examining historical tsunami records in the 1990s when he came across the detailed accounts of the January 1700 event. Using the physics of wave propagation, the mathematics describing how a wave generated by a seafloor displacement travels across an ocean basin, he calculated how long it would take for a tsunami originating off the Pacific Northwest coast of North America to cross the Pacific and reach Japan. The calculation was unambiguous, approximately 10 hours. He worked backward from the time the Japanese records showed the waves arriving. Subtracting 10 hours of ocean transit time, the source earthquake would have occurred in the evening hours of January 26, 1700, Pacific Standard Time. Satake collaborated with Brian Atwater and a team of colleagues on both sides of the Pacific. They cross-referenced the Japanese records with the carbon-dated ghost forests in Washington and Oregon. They compared the wave heights recorded in Japan with computer models of what different rupture sizes would produce at those distances. The numbers pointed to a single conclusion. Magnitude approximately 9, rupture extending the full length of the Cascadia Fault, January 26, 1700, evening hours. Every independent line of evidence agreed. The ghost forest confirmed by carbon dating to approximately 1700. The sand layers in the coastal marshes deposited by the inrushing tsunami dated to the same period. The oral histories of coastal indigenous nations describing exactly what a magnitude 9 earthquake followed by a tsunami would produce. The Japanese provincial archives recording the arrival time and height of waves consistent with a Cascadia source. This was one of the first times in history that a great earthquake was reconstructed entirely from proxy evidence, from the fingerprints it left in sediment and wood and water and memory without a single contemporary seismograph record. The methodology it established changed earth science permanently. But for our purposes, what the 1700 reconstruction does is something more immediate. It confirms beyond reasonable scientific doubt that the Cascadia Subduction Zone is capable of producing a full zone magnitude 9 megathrust earthquake. This was not always accepted. As recently as the 1970s and early 1980s, there were serious scientists who argued that Cascadia might be a weak coupling subduction zone, one that accommodates plate convergence through slow, steady sliding rather than through locked accumulation and periodic great ruptures. The absence of obvious large historical earthquakes in Europe, Puriums, were not here in 1700. The evidence was in the marshes, the evidence was in the trees, the evidence was in Japan, and the evidence said Cascadia ruptures with magnitude 9, and the last time it did, approximately 3 centuries passed in between. Here is the geological record in its full context. Scientists have drilled into the ocean floor off the Cascadia coast and sampled the sediment record going back 10,000 years. Within those sediments are turbidite layers, deposits of fine-grained material that cascade down the continental slope and settle on the deep ocean floor in the turbulent aftermath of a great earthquake. Each turbidite layer represents one major rupture event. The record shows approximately 40 such events over 10,000 years. 40 ruptures in 10,000 years. That suggests an average recurrence interval of roughly 200 to 500 years between major Cascadia earthquakes. The range is wide because the intervals vary. Some ruptures are separated by only a century, some by nearly 6 centuries. The fault does not operate on a strict schedule, but the average puts us, as of 2026, exactly within the window, 326 years since the last rupture, well inside the 200 to 500-year average range. We are not overdue in the way that implies the earthquake is imminent tomorrow. Seismologists are careful about that language, because probability does not work like a clock, but we are inside the statistical window during which a recurrence event is consistent with the geological record. The fault is loaded, the geological record says it ruptures in cycles, and the pressure that has been building in the locked zone since that night is now at a level that no living human being has ever experienced being released. There is one more thing to understand about the 1700 earthquake before we move forward. Something that changes how you should think about the silence that has followed it. When the fault ruptured in 1700, it did not rupture cleanly and uniformly along its entire length. Paleoseismic evidence suggests the rupture may have been more complex, different segments activating in sequence, different amounts of slip occurring at different locations. The ghost forest record, examined in detail, shows variation in the amount of land subsidence along the coast, which is consistent with a rupture that was not perfectly uniform. This complexity matters because it is directly relevant to the 2026 tier discovery, because what researchers found in the plate this year, the structural discontinuity running through the subducting slab, adds a new dimension of complexity to an already complex system. And the question it raises is not whether the fault will rupture again. The question it raises is when it does, which version of the rupture will we get? We are going to answer that question, but to understand the answer, you first need to understand the machine. The actual physical mechanism that makes Cascadia what it is, not the history, not the statistics, the engine itself, territory, Tadalas, that is what comes next. TCT3, the invisible machine. There is a machine running beneath the Pacific Northwest coast right now. It has been running without pause for 10 million years. It operates at a depth where no human has ever stood, where pressures are measured in tens of thousands of atmospheres, and temperatures are high enough to make rock flow. It has no moving parts in any sense you would recognize. It has no noise that carries to the surface. It produces nothing visible, nothing measurable, without specialized instrumentation. And it is building toward a moment of energy release that will be experienced across an area larger than most countries. The machine is called a subduction zone. Understanding how it works, not in vague general terms, but in the specific mechanical detail that explains why Cascadia behaves the way it does, is the difference between hearing about this fault on the news and actually understanding what it means. Here is the mechanism. The Juan de Fuca plate is a piece of oceanic crust. It is dense, cold at its surface, but warming as it descends, and old, formed at mid-ocean, spreading ridges where magma wells up from the mantle and creates new seafloor. As the North American continent moved westward over geological time, the Juan de Fuca plate, one of the fragments of the larger ancient Farallon plate, found itself on a collision course with that continent. The two plates met at what is now the Cascadia Subduction Zone. When an oceanic plate meets a continental plate, the oceanic plate loses. It is denser, it sinks, it is forced downward into the mantle beneath the lighter continental plate in a process called subducting. The Juan de Fuca plate is currently descending into the mantle beneath Western North America at roughly 4 centimeters per year. That descent has been continuous for millions of years, but the descent is not smooth. In the zone where the two plates first meet, the interface zone, just offshore at depths of roughly 5 to 40 kilometers, the plates do not simply slide past each other, they press together under enormous pressure. The friction between them, given the roughness of the contact surfaces and the immense weight of the overlying material, is sufficient to lock them together. The Juan de Fuca plate is trying to descend. The friction is preventing it from descending smoothly. Instead, the upper plate, North America, bends. It is dragged downward slightly by the locked lower plate. The coastal regions compress. The rock of the continental plate stores elastic strain, the way a bent steel spring stores energy. This locked interface is what seismologists call the seismogenic zone. It is the engine of the megathrust earthquake. At some depth, the plates become too hot and the friction changes character. The rock behaves plastically rather than elastically. The plates can slide more freely. Below that depth, the subduction zone does not produce great earthquakes. Above it, in the locked zone, the strain accumulates until the friction fails. When the friction fails, the lower plate does not gradually slide free. It snaps. The accumulated elastic strain releases all at once. The upper plate lurches seaward, rebounding from its bent position. The coastline, which had been slowly dragged downward by the locked fault for centuries, suddenly rises. The seafloor displaces and the water above it moves. This is the sequence that produced the 1700 event. This is the sequence that will produce the next event. The locked zone of the Cascadia Subduction Zone has been mapped using an elegant and indirect method. GPS stations positioned along the Oregon, Washington, and British Columbia coasts measure their own positions with millimeter precision continuously year after year. These stations are recording something that would be invisible to human perception but is unambiguous in the data. The coastline is being compressed and slowly dragged downward by the locked fault offshore. The measurements show the coast moving eastward and slightly downward, exactly what the model of a locked subduction zone predicts. The magnitude and direction of that motion matches what you would expect from a fault that is storing rather than releasing strain. The GPS data is in effect a slow-motion X-ray of the stress accumulation happening in the locked zone. And the data has been collected long enough to reveal something important. The locking is not uniform. This is where the physics becomes complicated and where the 2026 research becomes critical. Different sections of the locked zone are more or less strongly coupled. In some areas, the plates are essentially welded together, no sliding at all, maximum strain accumulation. In other areas, the coupling is partial, some slow sliding occurs, which bleeds off some strain, but not all. The 2026 study by a research team using 13 years of data from seafloor observatory sensors, instruments anchored directly to the ocean floor above the fault zone added new resolution to this picture. The sensors detected patterns of ground motion that revealed both the locked zones and the transitional zones with unprecedented clarity, and in that data, the researchers identified the tier, not in the locked zone itself. In the subducting plate, the Juan de Fuca slab, as it descends, a structural discontinuity in the plate that divides one section of the descending slab from another, a tear that runs through the plate the way a crack runs through a piece of wood before you break it across your knee. The tear is real, it is documented, it is the subject of a peer-reviewed paper in one of the world's leading earth science journals. Here is why it matters. When the fault ruptures, and the fault will rupture, the manner in which that rupture propagates along the fault plane depends partly on the structure of the descending plate. In a homogeneous slab, a rupture that starts in one location tends to propagate in predictable ways governed by the physics of shear failure. The models built over 4 decades of Cascadia research are based in part on assumptions about that propagation. But often, a tear in the slab changes those assumptions. It changes where a rupture might stop. It changes how energy might distribute between different fault segments. It changes the shape of the shaking footprint at the surface. And critically, it changes the tsunami generation profile because the shape and magnitude of the seafloor displacement that generates the tsunami depends on where the fault ruptures and how much it slips in different locations. None of this means the earthquake will be smaller. The strain in the locked zone does not know about the tear. The strain is accumulated in the upper plate and the shallow interface, not in the deep part of the descending slab. The tear affects the propagation dynamics. It does not drain the reservoir. The reservoir is full. We are going to look at exactly how full in the next chapter. But before we do, there is something I want to address directly, something that the mainstream understanding of Cascadia consistently gets wrong. A blind spot that has been built into how this fault is discussed in textbooks, in news reports, and even in some official risk communications. A blind spot that has been allowing people who live on the Pacific Northwest coast to feel safer than the data actually justifies. That blind spot is the subject of the next act. You have heard the Cascadia Subduction Zone described as a silent fault. You have probably heard that the lack of major earthquake activity in recent decades is on balance not particularly alarming, that the Pacific Northwest is well studied, that scientists have good models, that building codes have been updated, that the emergency management community is aware of the risk. All of that is true. None of it means what you think it means. There is a specific cognitive error built into how humans evaluate long-term geologic risk, and it is the same error that allowed tens of thousands of people to live in the shadow of Nevado del Ruiz in Colombia in 1985 without adequate preparation, and the same error that allowed coastal communities in the Indian Ocean basin to have no tsunami warning system in 2004, and the same error that kept the scientific community from accepting Cascadia's true hazard potential until the 1990s. Member, Bersosa da Anu. The error is this. We calibrate our sense of danger to the hazard signals we can perceive in our own lifetimes. If an earthquake has not occurred in the last 50 years, it feels safer than a fault that produces a small earthquake every decade. The absence of events reads as evidence of safety. But for a subduction zone like Cascadia, the absence of major events is not evidence of safety, it is evidence of storage. The 1964 Alaska earthquake should have ended this confusion. Prior to March 27, 1964, the fault beneath Prince William Sound in Alaska was considered geologically quiet. No major ruptures in the historical record, low seismicity on the main fault interface. Many geologists of the era believed that the subduction zone there was weakly coupled, not capable of a great earthquake. Then, at 5:36 in the afternoon, the fault ruptured along a section more than 800 kilometers long. The magnitude was 9.2. The shaking lasted approximately 4 minutes. The tsunami that followed reached as far as Crescent City in Northern California, killing people who had no warning and no understanding of what was coming from the north. It was at that time the most powerful earthquake ever recorded in North American history, and it came from a fault that had been considered essentially safe. Cascadia has the same quiet profile. The difference is that after 1964, after the Indian Ocean in 2004, after Tohoku in 2011, the scientific community now understands what that profile means. The understanding has been updated. The hazard maps have been updated. The building codes, slowly, incompletely, but meaningfully, have been updated. But public perception has not kept pace with scientific understanding. Ask most residents of Seattle what they know about the Cascadia Subduction Zone, and you will get one of two responses. Either a vague recognition that there might be a big earthquake someday, delivered with the same mild concern applied to a long-term weather forecast, or a confident belief that the earthquake is so far in the future, so statistically uncertain, that it does not warrant immediate personal action. Both of those responses are shaped by the same blind spot. The absence of recent catastrophic events reads as permission to focus elsewhere. The brain is built to respond to immediate, visible, tangible threats. A fault that has been silent for 326 years does not feel like an immediate threat, even when the probability mathematics says clearly that it is a present risk. This is the mainstream media failure as well. A magnitude 9 megathrust earthquake is not a news story until it happens. The daily, ongoing, relentless accumulation of strain in the Cascadia lock zone is not a news story. A new peer-reviewed paper in Science Advances about a tear in the subducting plate is not a news story on the 6 o'clock broadcast, but the 2011 Tohoku earthquake was a news story after it happened, after nearly 20,000 people were dead. The pattern is consistent. The lesson is not being learned quickly enough. There is a second layer to this blind spot that is more technical but equally important. The models most commonly used in public-facing risk communication for Cascadia are based on the assumption of a single, relatively coherent rupture along the full fault zone. A single great earthquake, magnitude 9 or thereabouts, producing a specific and modeled distribution of ground shaking and a specific and modeled tsunami propagation pattern. Emergency planning, evacuation route designation, building code standards, infrastructure retrofit prioritization, all of these have been developed against that modeled scenario. The 2026 tier discovery introduces a complication to that scenario that the models have not yet fully absorbed. If the tear causes the rupture to propagate differently than the standard model assumes, if it changes the slip distribution, the duration, the directivity of the seismic energy, then the ground shaking pattern at the surface may differ from what the hazard maps show. Certain areas might experience stronger shaking than predicted, others might experience less. The tsunami generation pattern might be altered in ways that change which communities have more or less warning time. The emergency plans built for the standard scenario may be the wrong plans for the actual scenario. This is not a criticism of the scientists or the planners. The models they built were the best possible models with the data available at the time, and the new data is being incorporated. The hazard maps will be updated, the planning scenarios will be revised, but those revisions take time. And in the gap between the new knowledge and the updated plans, there is a population of several million people living on the Pacific Northwest coast, making decisions about preparedness based on information that is already out of date. That gap is the blind spot, and it is the blind spot that the data we are about to look at makes most dangerous. Because the data from 2026 is not showing a stable, slowly accumulating hazard that we have decades to fully model and plan around. The data is showing something that is changing, something that is accelerating, something that has the full attention of the researchers who are closest to it. Every year, the Juan de Fuca plate moves 4 centimeters eastward. Every year, 4 centimeters of that movement is absorbed as elastic strain in the locked zone. Every year, the rubber band stretches a little further. This has been happening since 1700. The mathematics are simple and unforgiving. 326 years multiplied by 4 centimeters gives approximately 13 meters of accumulated slip deficit, 13 meters of movement that has not happened yet, 13 meters of displacement stored in the rock and the fault interface waiting to release. When that displacement releases, it will not release gradually. It will release in the form of fault slip, the upper plate moving sharply seaward, the seafloor displacing, the ground shaking with the energy of thousands of nuclear weapons detonated simultaneously. That is the baseline. That is the static picture of where Cascadia stands. But the 2026 data is showing something beyond the baseline, something that has changed the conversation among the researchers who are monitoring this fault in real time. It is called episodic tremor and slip. Deep beneath the locked zone, in the transition region, where the friction changes character and the plates begin to slide more freely, there is a phenomenon that was not discovered until 2001 and was not fully understood for years after that. In this deep transition zone, the fault experiences periodic episodes of very slow sliding, accompanied by swarms of very weak seismic signals called non-volcanic tremor. The sliding is too slow to produce strong shaking. The tremor is too weak to feel at the surface. For decades, this process was completely invisible to the monitoring tools available to scientists. When it was finally detected and characterized, it upended several assumptions about how subduction zones work. Episodic tremor and slip events in the Cascadia system recur approximately every 12 to 14 months. Each event represents a small release of strain in the deep transitional part of the fault. The amount of slip involved is measurable by GPS, a few centimeters of movement over weeks to months in the deep fault zone. Here is why this matters. The episodic tremor and slip events are occurring at the down-dip edge of the locked zone. They are happening immediately adjacent to, and in some models, partially overlapping with the region where the great earthquake strain is accumulating. Some researchers have argued that these deep slip events can, under certain conditions, transfer stress upward into the locked zone. That the stress loading of the locked zone is not a simple linear accumulation, but a dynamic process that may be being influenced by the behavior of the deep fault zone. In 2026, the cadence and character of these events have been measured with the precision that the seafloor and the picture they show is not of a fault in simple steady-state accumulation. It is a fault in which the stress distribution is dynamic, in which the boundary between the locked zone and the transitional zone is not a fixed line, but a migrating boundary that shifts with each tremor and slip cycle, in which the deep fault is doing something that has the attention of researchers who have spent careers studying this system. The GPS coastal deformation data tells a parallel story. Stations along the Oregon and Washington coast have been recording their positions for more than 2 decades. The time series from those stations shows the steady eastward and downward compression expected from a locked fault, but embedded in that signal, visible with modern processing techniques, are subtle variations, small departures from the linear trend that correspond to the episodic tremor and slip events below. The land is moving, not dramatically, not in a way you would feel standing on it, but measurably, repeatedly, in a pattern that is consistent with the fault system that is alive in ways that the simple static model does not capture. The 2026 Science Advances paper added another layer to this picture. The 13 years of seafloor sensor data analyzed in that study revealed that the degree of locking in the Cascadia fault zone is heterogeneous in both space and time. Different patches of the fault are more or less locked at different times. Fluid movement along the fault interface, water squeezed out of the subducting slab as it descends and heats, modifies the friction in ways that are detectable in the sensor data. This fluid dynamics component is important. In other subduction zones around the world, changes in fluid pressure along the fault interface have been associated with changes in seismic behavior, sometimes preceding major ruptures. The presence of measurable fluid movement in the Cascadia fault data is not evidence that an earthquake is imminent, but it is evidence that the fault is not simply a static accumulation machine. It is a dynamic system in which multiple variables are in play simultaneously. Consider what happens to a rock under the pressures involved in subduction. At the depths of the Cascadia Locked Zone, 5 to 30 kilometers below the surface, the temperature and pressure conditions begin to change the mineralogy of the subducting oceanic crust. Minerals that contain water in their crystal structure begin to break down. The water is expelled. It moves upward along fractures and through permeable rock toward the fault interface. When that water enters the locked zone, it modifies the effective stress on the fault. It reduces the friction between the plates in the right quantity, in the right location. Elevated pore fluid pressure can be the trigger that initiates slip where slip would not otherwise have occurred. This is not speculation. This mechanism is documented in multiple subduction zones around the world. The 2011 Tohoku earthquake in Japan, the deadliest natural disaster in that country in living memory, occurred in a fault zone where fluid migration had been identified as a factor in the stress loading of the locked interface. In Cascadia, the 2026 sensor data revealed fluid movement signatures that had not been clearly resolved in earlier datasets. The sensors, positioned on the seafloor directly above the fault, detected pressure and deformation signals consistent with episodic upward migration of pore fluids from the subducting slab. The researchers who analyzed this data did not conclude that rupture was imminent, but they noted in their discussion that the fluid dynamics component adds a variable to the system that has historically been associated with changes in fault behavior at other subduction zones. The system has more moving parts than the simplified model assumed. The tear in the plate is one variable, the episodic tremor and slip is another, the fluid dynamics is a third, and underlying all of them is the primary variable that has not changed since 1700, 326 years of accumulated strain in a locked zone that history tells us will eventually inevitably fail. The ledger is not just full, the ledger is complicated. And there is one more dimension to this complexity that we have not yet addressed. It concerns the timing of the episodic tremor and slip cycles relative to the overall hazard picture. In the Cascadia system, the tremor and slip events occur at depths of 25 to 45 kilometers deeper than the locked zone, in the region where the fault transitions from locked behavior to stable sliding. The most recent sequence, which ran from late 2024 through early 2025, was notable for its geographic extent. It migrated along a longer segment of the fault than the preceding events, from a starting point in northern Washington southward through Oregon over a period of approximately 3 weeks. Researchers who study these sequences note that longer, more extensive tremor and slip episodes may indicate changes in the stress distribution in the deep fault zone. The 2026 paper incorporated the data from that sequence into its broader analysis and found that the pattern of deep fault activity was consistent with the heterogeneous locking picture described by the seafloor sensors. In plain language, the deep part of the fault is not behaving the way a simple, uniform subduction zone would behave. And the shallow locked zone, where the great earthquake energy is stored, sits directly above this complex, dynamic deep zone, feeling every change in the stress regime below it, responding to every episode of deep tremor and slip with its own subtle adjustments to the strain distribution. The system is not static, it has not been static, and the 2026 data has for the first time given researchers the resolution to see that non-static behavior clearly enough to characterize it. What they see is a machine that is more sophisticated than the original model, a machine with feedback loops between its deep and shallow components. A machine whose behavior is influenced by fluid migration, by structural discontinuities, by the asymmetric geometry of the descending slab. A more sophisticated machine does not mean a less dangerous one. In this case, it means precisely the opposite. And in the next chapter, we are going to look at what happens when a complicated ledger produces a result that the models predicted, but not in the form they predicted it. For 3 weeks in late February and early March of 2026, something happened in the scientific community that does not happen very often. A finding emerged that appeared at first reading to be genuinely good news about Cascadia, not a reduction in the overall hazard, not a finding that the fault was less dangerous than previously thought, but a finding that might suggest the next rupture would be smaller than the worst-case scenario. The preprint of the Science Advances paper began circulating in geoscience networks in late February. The key finding, the tear in the subducting plate, was initially interpreted by several commentators as a potential limiting factor for rupture propagation. The logic was straightforward. If the plate has a structural discontinuity, that discontinuity might act as a barrier to rupture propagation, causing the earthquake to terminate when it reaches the tear rather than continuing through it. Smaller rupture, smaller earthquake, smaller tsunami. For approximately 72 hours, this interpretation spread through secondary science communication channels. It appeared in summaries. It was cited in discussions. The word good news was used. The scientific community exhaled, and then the paper was read more carefully. The actual conclusion of the peer-reviewed study, the conclusion that the authors themselves drew, in the careful, precise language of scientific literature, was something substantially different from the good news framing. The conclusion stated that the tear adds complexity to the rupture scenario. It stated that different segments of the fault, separated by the tear, might behave differently in a future rupture, potentially rupturing separately in different events, or potentially rupturing together in a cascading sequence. The conclusion stated that the tear does not reduce the strain stored in the locked zones on either side of it. Those locked zones are still locked. They are still accumulating strain at 4 centimeters per year. Nothing about the tear changes the energy in the vault. What the tear changes is the key. The tear makes the vault's opening mechanism harder to predict. In a fault without the tear, models can estimate with some confidence how a rupture initiated at one point will propagate along the fault. The physics are well constrained by decades of study and by comparisons with other subduction zones. The hazard maps produced from those models have a known and characterized uncertainty. In a fault with a tear of this kind, the rupture propagation options multiply. The earthquake might initiate on one side of the tear and stop there, producing a partial rupture. It might cross the tear. It might trigger a delayed rupture on the other side of the tear, producing a sequence of large earthquakes rather than a single great one. Any of these scenarios produces a different ground-shaking footprint. Any of them produces a different tsunami. The emergency plans built for the standard full-zone rupture scenario are not wrong for that scenario. But if the actual event is a partial rupture or a segmented rupture or a sequence of ruptures, the plans may be optimized for a scenario that does not occur. The evacuation routes designed around a particular tsunami inundation zone may not match the actual inundation. The buildings retrofitted to withstand a particular ground motion intensity may be in the wrong location relative to the actual shaking pattern. This is not a hypothetical problem. This is what the researchers who wrote the 2026 paper are saying directly in their conclusions. The seismic hazard in the Cascadia region has not decreased as a result of the tear discovery. It has become less certain, and in the language of risk management, less certain does not mean safer. Less certain means the tails of the probability distribution are wider. Less certain means the worst-case scenario is harder to bound. Less certain means the planning assumptions require revisiting. The brief exhale, the 72 hours of cautious optimism that followed the initial circulation of the preprint was premature. The fault is not more benign than we thought. The fault is more complex than we thought. And complex faults in the history of seismology are not the ones that produce smaller earthquakes. They are the ones that produce surprises. The next chapter examines what the surprise looks like when it arrives, not in abstract probabilistic terms, in real time, in human terms, on a specific, ordinary afternoon on the Pacific Northwest coast. ACT 7, when the ledger close, consider the geography. From northern California to the southern tip of Vancouver Island, the Pacific Northwest coast is home to some of the most economically significant and densely populated metropolitan areas in North America: Seattle, Portland, Vancouver, Tacoma, Eugene, Victoria. Combined, the urban zones within the primary Cascadia impact area hold a population of approximately 10 million people, with several million more in the surrounding regions that will experience secondary effects. The I-5 corridor, the highway spine running from the Canadian border through Seattle and Portland to the California line, carries the majority of overland freight movement for the entire Pacific Northwest. Agricultural products, timber, industrial goods, consumer imports from the Pacific Rim. All of it moves on I-5 and the parallel rail lines that follow roughly the same alignment. The ports of Seattle and Tacoma are two of the most active container ports on the west coast of North America. Together, they handle tens of millions of tons of cargo annually. Much of what moves through them connects Pacific Rim manufacturing, particularly electronics and consumer goods from East Asian suppliers, to North American distribution networks. The seaport infrastructure is built on land that in many cases sits on liquefiable soil adjacent to tidal water. The terminal structures, the cranes, the warehousing, the access roads, all of it is in the zone of maximum ground motion exposure in a Cascadia event. Now consider what a magnitude 9 Cascadia rupture does to that geography. The shaking begins offshore and propagates inland at the speed of seismic waves. Sex waves, the shear waves that produce the strongest ground motion at the surface, travel at several kilometers per second. They reach the coast within tens of seconds of the rupture initiation. Within 1 to 2 minutes, strong shaking is occurring throughout the Seattle metropolitan area. Within 3 to 4 minutes, Portland is experiencing maximum ground motion. The shaking does not last 10 seconds. It does not last 30. For a magnitude 9 event, the duration of strong ground motion in cities close to the rupture zone can be 2 to 4 minutes. 2 to 4 minutes of ground moving in ways that most buildings were not designed to withstand, particularly older structures built before updated seismic codes were implemented. Seattle has a significant inventory of unreinforced masonry buildings, older commercial and residential structures whose walls are brick or concrete block without the steel reinforcement that modern seismic design requires. These buildings perform poorly in large earthquakes. Their walls crack and collapse, their floors lose support. The occupants of these buildings during strong extended ground motion are in serious danger. Portland faces a similar challenge. The city has been working to identify and retrofit unreinforced masonry buildings. Progress has been made. The work is not complete. The bridges are a separate category of concern entirely. The Pacific Northwest has hundreds of bridges crossing rivers, inlets, and tidal channels throughout the metropolitan areas and along the highway corridors. Many were designed and built before modern seismic engineering standards were established. Their foundations may be in liquefiable soils. Their approaches may experience differential settlement during strong shaking. Some will survive a major Cascadia event, others will not. The failure of a single bridge on a critical evacuation route does not merely inconvenience the people who need to use that route, it eliminates it. And in a post-earthquake environment, where roads are damaged, where debris is present, where traffic is chaotic, and emergency services are overwhelmed, a single failed bridge can strand thousands of people in an inundation zone. The supply chain consequences extend far beyond the Pacific Northwest. The ports of Seattle and Tacoma are not simply regional facilities, they are nodes in a global logistics network. When they go offline, and in a major Cascadia event they go offline, the goods that normally flow through them need to reroute to Los Angeles, to Vancouver, BC, if it is not also damaged, to East Coast ports with insufficient capacity to absorb the additional volume. The rerouting takes time, weeks, possibly months, before alternative routes reach full capacity. During that time, the supply chains that depend on West Coast port access are disrupted. The specific categories most affected include consumer electronics, which move predominantly through Pacific ports, automotive parts for manufacturing facilities throughout North America, agricultural exports from the Pacific Northwest, including timber products and Pacific salmon, medical device supply chains with Pacific Rim sourcing, technology hardware for data centers concentrated in the Pacific Northwest. The economic modeling of a full Cascadia rupture has been attempted by several research groups and emergency management agencies. The figures vary depending on assumptions, but they consistently arrive at numbers measured in hundreds of billions of dollars of direct damage and economic disruption. Some models, incorporating the full supply chain and secondary economic effects, have produced estimates in excess of $1 trillion. For context, that is larger than the gross domestic product of most countries, and that is before the human cost. The British Columbia Provincial Assessment modelled the human impact of a magnitude 9 Cascadia scenario and described in plain language what the minutes after the rupture would look like. Thousands dead or injured in the initial shaking, coastal communities swept by tsunami waves arriving within minutes, infrastructure, bridges, hospitals, water treatment facilities, power distribution systems simultaneously damaged across a geographic area so large that mutual aid from unaffected regions is severely limited. The closest analogue the report cited was the 2004 Indian Ocean earthquake and tsunami, which killed more than 230,000 people across 14 countries. The report noted that Cascadia, in terms of its tectonic setting, rupture length, and tsunami generation potential, is directly comparable to the 2004 event. That comparison was not made for rhetorical effect. It was made because it is the most scientifically valid reference point in the historical record. British Columbia has evacuation drills, it has warning systems, it has building codes that are better than what existed along the Indian Ocean in 2004. Those advantages matter. They will save lives, but the underlying physics is the same, and the coastline is full of people who on a typical Tuesday afternoon are not thinking about any of this. The ferry leaving Swartz Bay, the school group at Pacific Rim National Park, the fishing boats off Uclate, the hikers on the trails above the Strait of Juan de Fuca. They have somewhere between 8 and 20 minutes. Let us look at those minutes. Imagine a clear afternoon in late July. The forecast along the British Columbia coast is favourable, winds calm, visibility excellent, the kind of day that makes the Pacific Northwest feel like the most beautiful place on Earth. A BC Ferries vessel is approximately 4 kilometres out of Swartz Bay Terminal, heading north through the Saanich Inlet, carrying 273 passengers and crew, several dozen cars on the vehicle deck below. At Pacific Rim National Park on the west coast of Vancouver Island, a school group of 31 students and 4 teachers is on the beach at Long Beach. The tide is going out, the kids are collecting shells. In the waters off Ucluit, 2 commercial fishing vessels are working the salmon grounds, radio on, no weather alerts, a normal fishing day. In a downtown Victoria office building, 14 floors of government and insurance company employees are at their desks. At 2:47 in the afternoon, the Juan de Fuca plate slips. The rupture initiates approximately 80 kilometres offshore, at a depth of roughly 20 kilometres, in the most locked segment of the fault interface. Within seconds, the break begins propagating northward and southward along the fault plane. The propagation is rapid, kilometres per second, driven by the enormous elastic energy stored in the locked zone. The rupture propagates for 2 minutes, before the full extent of the broken surface is established. By the time it stops, approximately 900 kilometres of fault have ruptured. The average slip on the fault plane is 15 metres. In some segments, it is more. The seafloor rises by up to 6 metres along portions of the rupture's inlets. 1. The first seismic waves reach the surface within seconds of the rupture's initiation. People waves. The compressional waves that travel fastest through rock arrive at the coast with a sharp jolt, like a sudden impact. The people waves alone are strong enough to knock objects off shelves, to alarm people, to trigger an immediate awareness that something significant is happening. Approximately 5 to 10 seconds after the people waves, the cess waves arrive. This is when the ground begins to move in ways that are difficult to describe to someone who has not experienced a large earthquake. Not a sharp jolt, a sustained, deep swaying motion, with multiple frequencies superimposed on each other. The long period motion of large surface waves rolling through the crust. The shorter period shaking of the direct S waves. All of it simultaneous, all of it strong, all of it continuing and continuing. At the 30-second mark, the shaking has not stopped. At the 1-minute mark, the shaking has not stopped. People who have been trained, who know to drop, cover and hold on, are doing so. People who have not been trained are making decisions in extreme stress with insufficient information. At the 90-second mark, the shaking has not stopped. In downtown Victoria, the 14-storey office building is experiencing ground motion at the upper end of its design envelope. Some damage to interior finishes, no structural failure, but the elevator system has automatically shut down. Power has gone out, emergency lighting is on, and unreinforced masonry buildings elsewhere in the city, the situation is different. Brick facades are cracking. In some buildings, partial wall collapses are occurring. People near exterior walls are being injured by falling masonry. At the 2-minute mark, the shaking begins to diminish, not immediately to nothing. The tail of the shaking, the late arriving surface waves, continues for another minute or two at reducing intensity. But the peak ground motion is past. It has been approximately 2 minutes of strong shaking, 2 minutes that have damaged hundreds of buildings across southern Vancouver Island and the Gulf Islands, 2 minutes that have broken water mains, ruptured gas lines, disrupted electrical distribution, damaged several bridges, and covered multiple roads with debris from collapsed structures and landslides. Now the clock starts. The seafloor displacement that occurred when the fault slipped has generated a tsunami. The wave is propagating outward from the rupture zone in all directions. The portion of the wave moving eastward toward the British Columbia and Washington coasts is moving at the speed appropriate to the water depth. In deep water, that speed is comparable to a commercial jetliner. On the outer coast of Vancouver Island, the sea is doing something. The tidal channels and inlets are draining. Water is being drawn seaward, pulled by the leading trough of the approaching tsunami. The ocean is withdrawing from beaches that should be covered at this stage of the tide. The fishing vessels off Ucluelet are watching the water level drop around them, exposing reefs that should be submerged. This is the warning. This visible recession of the sea is the natural warning signal that has been recognized by coastal peoples for thousands of years. If you see the sea withdraw suddenly and dramatically, you do not go to the beach to look at the exposed sea floor, you go to high ground immediately. Approximately 8 minutes after the rupture, the first wave reaches the outer coast of Vancouver Island. It is not one wave, it is a series. The leading wave may not be the largest. The succession of crests and troughs continues for hours, with the largest waves potentially arriving in the second or third wave of the sequence. The height of the waves on the outer coast is modelled at between 10 and 20 metres in some locations, depending on the offshore bathymetry, the underwater topography, which focuses and amplifies the wave energy in some areas and diffuses it in others. Coastal communities on the outer coast, Tofino, Ucluelet, Port Renfrew, communities along the west coast of Vancouver Island, are in the primary tsunami impact zone. For these communities, the window between the end of the shaking and the arrival of the first wave is measured in minutes. Some communities have formal evacuation plans. Some have vertical evacuation structures, buildings designated as assembly points above the projected inundation level. Whether those plans and structures perform as intended depends on a combination of factors, including how much the earthquake damages the evacuation routes, how quickly the community responds, and whether the shaking itself injures or incapacitates people who would otherwise evacuate. The school group on the beach at Long Beach becomes aware of the wave before it arrives because the beach in front of them has emptied. The ocean has withdrawn to a distance that none of the children have ever seen before. The teachers who have been trained in tsunami response begin moving the group immediately toward the tree line and toward higher ground. The students who have participated in school earthquake and tsunami drills know what to do. They move. Whether they have enough time depends on where they are on the beach, how mobile all 31 students are, and exactly how the wave sequence develops. In the Saanich Inlet, the BC Ferries vessel is in a more protected location. The tsunami energy is partially blocked and attenuated by the topography of the inlet. The shaking, however, caused the vessel to roll and lose stability momentarily, injuring several passengers. The ferry is proceeding at reduced speed, attempting to contact the terminal operating on backup communications. The tsunami is entering the strait, where its energy is being channeled and modified by the narrowing of the passage. Communities on the shore of the strait, on both the Canadian and American sides, are watching the water with alarm. 19 minutes after the rupture, the tsunami reaches the Washington coast. Communities at lower elevations in the primary inundation zones are receiving water. The earthquake has been over for 17 minutes. The emergency response has barely begun. Communications infrastructure is severely degraded. The cell network, which depends on power and on base stations that are themselves in earthquake-affected zones, is intermittent. Emergency services are simultaneously receiving calls from every direction. Hospitals are activating mass casualty protocols while their own facilities have sustained damage. The first 72 hours after a Cascadia rupture represent what emergency managers call the acute phase, the period in which immediate life safety actions, search and rescue, evacuation, medical triage, shelter establishment are the overwhelming priority. During that period, the ordinary systems on which urban life depends, electricity, water, natural gas, telecommunications, transportation, food distribution, are simultaneously disrupted across an area that encompasses several major cities and hundreds of smaller communities. External help arrives slowly because the routes into the affected zone are themselves damaged, because the requesting agencies are themselves in the disaster, and because the scale of the event exceeds any pre-positioned response capacity. This is not a failure of planning or of people. It is the arithmetic of a magnitude 9 earthquake. The arithmetic is what it is. Let me walk through what those 72 hours actually look like, because the numbers in the damage models are not abstract. They have names and addresses. At the 6-hour mark, emergency services across the Pacific Northwest are working at maximum capacity in every direction simultaneously. Search and rescue teams are being deployed into collapsed structures in Victoria and Nanaimo and the Fraser Valley. The Provincial Emergency Management Agency is attempting to establish communications with coastal communities that have gone completely silent. The silence is not a communications failure. The communities are underwater. At the 12-hour mark, the aftershock sequence has begun in earnest. The main shock at magnitude 9 is followed within hours by aftershocks in the magnitude 7 and 8 range. These are not trivial events. A magnitude 7 aftershock is itself a major earthquake by any ordinary standard. It will damage structures that survived the main shock. It will trigger additional landslides on slopes that were destabilized by the initial shaking. It will collapse walls that were cracked but standing. Emergency responders working in damaged buildings face renewed hazard with each major aftershock, and there will be many in the days following a magnitude 9 rupture. At the 24-hour mark, the full picture of the tsunami damage along the outer coast is beginning to emerge. Aerial reconnaissance, if weather permits, is showing the extent of the inundation. Communities like Tofino and New Cluset, popular tourist destinations in normal times, communities that tens of thousands of visitors pass through each summer, have sustained catastrophic damage in the inundation zone. The question of how many people were above the inundation line when the wave arrived depends on how well the self-evacuation worked in the 13 to 20 minutes between the end of the shaking and the first wave. At the 48-hour mark, the operational challenges shift from acute rescue to sustained emergency response. Potable water is unavailable across large portions of the affected region. Water treatment infrastructure runs on electricity, and the power grid is down across hundreds of kilometers of territory. The emergency water supply, pre-positioned reserves, trucked in bow. Tuttled water, military logistics is being mobilized but cannot fully close the gap for a population of several million people for more than a few days. At the 72-hour mark, the first external aid convoys are moving into the affected region along routes that have been cleared of debris and assessed for structural integrity. The rate of external aid arrival is still well below what is needed. The people who prepared, who have 72 hours of water, food, medication, and self-sufficiency, are in a fundamentally different position from those who did not. The preparation gap is the human story of Cascadia. It is the part that is not determined by the geology, and here is what matters about understanding it. The people who will navigate those 72 hours best are the ones who understood before the event what to expect, who made decisions before the event about where to be and how to respond, and who have the specific knowledge that turns confusion into action. That knowledge is available. It is not secret. It is not complicated. In the next 2 chapters, we are going to look at it directly. First, the real-time data, what you can read right now on publicly available monitoring platforms to understand the current state of the fault. Then, the specific concrete preparation steps that close the gap between knowledge and survival, ACT9, the real-time decoder. The data that monitors the Cascadia Subduction Zone is publicly available. It is not behind a paywall. It does not require a scientific degree to access. The primary monitoring platforms, the Pacific Northwest Seismic Network, the United States Geological Survey, and the GPS monitoring networks operated by UNAPSCO and Natural Resources Canada, all have public interfaces that are updated in real time, continuously, around the clock. Most people have never looked at them. That is about to change. Let me walk you through what the data actually shows, and more importantly, what to look for in it. The Pacific Northwest Seismic Network, which you can access at pnsn.org, operates hundreds of seismographs throughout Washington, Oregon, and Western Canada. The network's real-time display shows earthquake activity across the entire Pacific Northwest, updated continuously. The map is filterable by time range and magnitude. When you open that map and look at the offshore Cascadia Zone, you are going to see relatively little activity compared to other regions. Compared to the Puget Sound area, compared to the Cascades volcanic arc, compared to the plate boundary zones to the north and south, that relative quiet is the signature of the locked zone we have been discussing. But there is activity to look for. The episodic tremor and slip events, which occur in the deep transition zone below the main locked interface, produce a characteristic pattern of non-volcanic tremor. These appear on the PNSN tremor catalogue as clusters of very weak signals, typically distributed along the down-dip edge of the locked zone. The PNSN maintains a specific tremor catalogue that is accessible on their website and that shows the history and current status of tremor activity under the Pacific Northwest. When the next episodic tremor and slip episode begins, and based on the roughly 12 to 14-month recurrence pattern one will occur within the next year, you will be able to see it on that catalogue. The tremor appears as a swarm of low-frequency signals that migrate slowly along the fault from north to south or south to north over days to weeks. Again, tremor and slip is not the same as watching for the earthquake. Deep tremor and slip does not cause the megathrust rupture, but it is a window into the activity of the fault system at depth. It is the seismologist's version of listening to the building creak before asking whether the foundation is sound. The GPS data is a different kind of signal. The UNAVSICO PBO Plate Boundary Observatory operates a network of continuous GPS stations throughout the Pacific Northwest. The data from these stations is publicly available through the UNAVSICO website. Each station provides a time series of its position in 3 dimensions, updated daily. The specific signal to look for is the horizontal velocity of coastal stations in the direction perpendicular to the coastline, roughly east-west in this context. Stations on the Oregon and Washington coast should be moving eastward and slightly downward relative to stations in the stable interior of the continent. This eastward motion is the geodetic signature of interseismic strain accumulation, the upper plate being compressed by the locked fault below. The long-term rate is known. What would be significant, worth noting, worth paying attention to, is any deviation from that rate, a sudden acceleration, a reversal, a period of anomalously fast coastal motion followed by a period of anomalously slow motion. These deviations can occur during episodic tremor and slip. They can also occur in more subtle form in the period before major subduction zone earthquakes. Not always. Not reliably enough to constitute a warning system, but real enough that researchers track them and that changes in the pattern are documented and discussed. I want to be precise about what I am saying here, because precision matters. I am not telling you that watching the GPS data will tell you when the earthquake is coming. The science does not support that claim, and I will not make a claim the science does not support. What I am telling you is that the GPS data, the tremor catalogue, and the seismic monitoring all together give you a picture of the fault system's current state. They are the instrument panel for a machine that is operating in the basement of the continent. Reading the instrument panel does not tell you exactly when the machine will fail. But understanding the instrument panel is the difference between being surprised by the failure and being informed about it. There is a third data stream that is worth understanding, and it is the one that is most likely to appear in public discussion in the coming months and years as the 2026 research is absorbed by the broader community. It is the B value. In seismology, the B value is a parameter that describes the ratio of small earthquakes to large earthquakes in a given region and time period. In normal conditions, for every tenfold increase in earthquake magnitude, there are approximately 10 times fewer earthquakes. This relationship, described by what is called the Gutenberg-Richter law, holds reasonably well across most seismic regions in the world. A decrease in the B value, relatively fewer small earthquakes compared to the expected distribution, can be associated with increased stress in a fault zone. It suggests that the rock is under stress that is suppressing the small event activity. It is one of several parameters that researchers monitor as a potential precursor to larger events. For the Cascadia offshore zone, calculating B values is difficult because there are so few earthquakes of any kind to work with. The locked zone is quiet, but the research community is using the new seafloor sensor data to improve this analysis, and the results of that improved analysis are being closely watched.
If you want to understand the current state of Cascadia at any point in time, you have the tools, you have the public data platforms, you have the terminology to understand what those platforms are showing. That knowledge is the foundation of the final thing we need to discuss, what to do with it.
ACT 10. The ledger is yours now. Everything we have covered in this documentary comes down to a single practical question. What do you do with this information? Not as a society, not as a policy problem, as an individual or a family or a community, confronting the fact that a geological system of enormous power is accumulating energy in a region where people live, where critical infrastructure operates, where lives depend on systems that will be severely disrupted when the fault eventually speaks. The answer is not panic. Panic has never helped anyone survive a natural disaster. The answer is not fatalism. Fatalism, the belief that nothing you do matters because the outcome is determined, is also not supported by the evidence. In every major earthquake and tsunami event in recorded history, the people who had specific knowledge of what was happening and what to do with that knowledge had materially better outcomes than those who did not. In the same region, the village of Anioshi, whose residents had maintained a warning tablet from a 1933 tsunami inscribed with the instruction, "Do not build homes below this point," experienced 0 tsunami deaths. They were above the inundation line. The knowledge had been preserved. The knowledge was used. Tsason, the answer is preparation, specific, practical, grounded preparation built around what the science actually says is likely to happen and what actions actually improve outcomes. Here is what the science says, Tunashing, who Sakorton, the Boligo Tomod Mudiuld. The vast majority of people who are in modern, well-maintained structures, if they take the protective action, drop, cover and hold on, away from windows, under a sturdy desk or table if possible, in an interior doorway or against an interior wall if nothing else is available. The worst injuries from building interior shaking come from falling objects and broken glass. Protective posture significantly reduces that risk. Stay down and hold on until the shaking has been completely over for a significant amount of time. In a magnitude 9 event, the shaking will last minutes. Do not stand up because you think it might be over. Wait until you are certain. After the shaking stops, if you are on the coast or in a low-lying area adjacent to tidal water, assume a tsunami is coming, regardless of whether you have received any official warning. The shaking itself is the warning. The long duration of strong shaking is the warning. Do not wait for a siren. Move to high ground immediately on foot. Do not take your car unless your evacuation route is entirely on high ground and completely away from other traffic. In the aftermath of the shaking, roads may be blocked, bridges may be impassable, and traffic will be chaotic. Walking uphill is often faster and more reliable than driving. Know where high ground is before the event. Walk your evacuation route before the event. Know how long it takes you to reach safety at a normal pace and plan for conditions where that pace may be reduced by damage, debris, and the physical effects of the shaking itself. The 72-hour preparedness standard, maintaining supplies sufficient for 3 days of self-sufficiency, is widely recommended by emergency management agencies and is the recognized baseline for individual preparedness. Water at 1 gallon per person per day, non-perishable food, medications, first aid supplies, a battery-powered or hand-crank radio, flashlights, copies of essential documents, cash in small bills because electronic payment systems will not function without power. This is the minimum. For Cascadia, in light of the scale of the expected disruption to critical infrastructure, extending that baseline to 7 to 14 days of supplies is the more appropriate standard. The Great British Columbia Shakeout, which runs annually each autumn, is the world's largest earthquake drill. It trains participants in the drop, cover, hold-on response and raises awareness of earthquake preparedness more broadly. Participating in it and in the parallel shakeout programs in Washington and Oregon is one of the most practical things residents of the Pacific Northwest can do to prepare. There is a deeper question beneath all of this that I want to end with. Not a practical question, a philosophical one. We are living in a period in human history when our capacity to understand the physical systems of this planet, their history, their mechanics, their future trajectories, has never been greater. We can read the history of a fault in the rings of a 300-year-old dead tree. We can hear the deep tremor of a locked subduction zone through instruments on the ocean floor. We can reconstruct an earthquake that occurred before modern instrumentation existed, using records preserved in a country on the other side of an ocean. We are extraordinarily good at understanding these systems. We are less good at acting on that understanding. The gap between what science knows about Cascadia and what public policy, infrastructure investment, and individual preparation reflect about that knowledge is real. It has narrowed in recent decades. Building codes are better. Emergency planning is more sophisticated. Awareness has grown, but the gap is not closed. The Oregon Department of Emergency Management has published the 37% probability. The British Columbia government has published the risk assessment. The federal agencies of both countries have documented the hazard in peer-reviewed literature and in official planning documents. The next Cascadia earthquake will happen for the same reason. No policy will prevent it. No amount of awareness will stop the plates from moving. But the human story of that earthquake, who survives it, how the region recovers, how quickly infrastructure is restored, how many people were above the inundation line when the wave arrived, that story is not yet written. And the people who understand what is happening under that Pacific coastline, the people who have looked at the data and understood the mechanism and prepared accordingly, are the ones who get to write a better version of that story. 326 years of silence. The fault does not know how long it has been waiting. It does not have a calendar. It is not impatient or eager. It simply accumulates and releases and accumulates again on the time scale of the Earth itself. But we have calendars, we have the data, we have the ghost forests and the Japanese archives and the GPS stations and the seafloor sensors and the peer-reviewed papers. We have all the information we need to make better decisions than the people who stood on those beaches in 1700 with no warning at all. There is a concept in emergency management called the preparation paradox. It goes like this. The people who prepare most thoroughly for a disaster are the ones who think most carefully about its probability. But thinking carefully about probability requires accepting that the bad outcome is genuinely possible. And accepting that the bad outcome is genuinely possible is uncomfortable. So most people are violent adjacent to tidal water assume a tsunami is coming regardless of whether you have received any official warning. The shaking itself is the warning. The long duration of strong shaking is the warning. Do not wait for a siren. Move to high ground immediately on foot. Do not take your car unless your evacuation route is entirely on high ground and completely away from other traffic. In the aftermath of the shaking, roads may be blocked, bridges may be impassable, and traffic will be chaotic. Walking uphill is often faster and more reliable than driving. Know where high ground is before the event. Walk your evacuation route before the event. Know how long it takes you to reach safety at a normal pace and plan for conditions where that pace may be reduced by damage, debris, and the physical effects of the shaking itself. The 72-hour preparedness standard, maintaining supplies sufficient for 3 days of self-sufficiency, is widely recommended by emergency management agencies and is the recognized baseline for individual preparedness: water at 1 gallon per person per day, non-perishable food, medications, first aid supplies, a battery-powered or hand-crank radio, flashlights, copies of essential documents, cash in small bills, because electronic payment systems will not function without power. This is the minimum. For Cascadia, in light of the scale of the expected disruption to critical infrastructure, extending that baseline to 7 to 14 days of supplies is the more appropriate standard. The Great British Columbia Shakeout, which runs annually each autumn, is the world's largest earthquake drill. It trains participants in the drop cover hold-on response and raises awareness of earthquake preparedness more broadly. Participating in it, and in the parallel shakeout programs in Washington and Oregon, is one of the most practical things residents of the Pacific Northwest can do to prepare. Not a practical question, a philosophical one. We are living in a period in human history when our capacity to understand the physical systems of this planet, their history, their mechanics, their future trajectories, has never been greater. We can read the history of a fault in the rings of a 300-year-old dead tree. We can hear the deep tremor of a locked subduction zone through instruments on the ocean floor. We can reconstruct an earthquake that occurred before modern instrumentation existed, using records preserved in a country on the other side of an ocean. We are extraordinarily good at understanding these systems. We are less good at acting on that understanding. The gap between what science knows about Cascadia and what public policy, infrastructure investment, and individual preparation reflect about that knowledge is real. It has narrowed in recent decades. Building codes are better. Emergency planning is more sophisticated. Awareness has grown, but the gap is not closed. The Oregon Department of Emergency Management has published the 37% probability. The British Columbia government has published the risk assessment. The federal agencies of both countries have documented the hazard in peer-reviewed literature and in official planning documents. The information is not hidden. The 1700 earthquake happened because the physics of tectonic stress demanded it. The next Cascadia earthquake will happen for the same reason. No policy will prevent it. No amount of awareness will stop the plates from moving. But the human story of that earthquake, who survives it, how the region recovers, how quickly infrastructure is restored, how many people were above the inundation line when the wave arrived, that story is not yet written. And the people who understand what is happening under that Pacific coastline, the people who have looked at the data and understood the mechanism and prepared accordingly, are the ones who get to write a better version of that story. 326 years of silence. The fault does not know how long it has been waiting. It does not have a calendar. It is not impatient or eager. It simply accumulates and releases and accumulates again on the time scale of the Earth itself. But we have calendars, we have the data, we have the ghost forests and the Japanese archives and the GPS stations and the seafloor sensors and the peer-reviewed papers. We have all the information we need to make better decisions than the people who stood on those beaches in 1700 with no warning at all. There is a concept in emergency management called the preparation paradox. It goes like this. The people who prepare most thoroughly for a disaster are the ones who think most carefully about its probability. But thinking carefully about probability requires accepting that the bad outcome is genuinely possible, and accepting that the bad outcome is genuinely possible is uncomfortable. So most people avoid thinking carefully about probability, and so most people do not prepare. The preparation paradox is not a character flaw. It is a feature of how the human mind manages the psychological weight of living alongside risk that cannot be eliminated. We are not built to hold a 37% probability in our conscious attention indefinitely. The brain resolves that discomfort by reclassifying the risk as distant, improbable, someone else's problem. The solution to the preparation paradox is not to force yourself to feel the fear continuously. That is not sustainable and not helpful. The solution is to take the specific time-bounded actions that preparation requires, gather the supplies, walk the evacuation route, have the family conversation about the meeting point after an earthquake, and then allow yourself to live without the weight of it, knowing that you have done what is in your power to do. That is what the Aniyoshi villagers did. They read the stone tablet, they understood the flood history, they built above the line, and then they lived their lives on the hillside, not in chronic fear of the sea, but in the calm that comes from having made the right decision in advance. That is the version of Cascadia preparedness that this documentary is arguing for, not panic, not fatalism, not the compulsive checking of seismic monitors at 3 a.m. The informed decision made once that changes the outcome. Walk your evacuation route this week, time it, do it with your family, find the high ground, know where the water is stored, have the conversation. And then, and this is important, tell someone else. The most effective preparedness is community preparedness. The communities along the Pacific Northwest coast that will do best in the hours and days after a Cascadia rupture are the ones where neighbours have talked to neighbours, where the school has run the drill, where the local government has published and promoted the evacuation plan, where the culture of preparedness has been built not through fear, but through shared understanding of a shared risk. That culture is built one conversation at a time. This documentary is one of those conversations. The ledger has been open for 326 years. What you do with that knowledge is the only part of this story you control. The plates are moving right now as you listen to this. 4 centimeters per year. The locked zone is holding. The vault is full. The machine is running as it has run for 10 million years, without pause and without mercy, in the dark beneath the Pacific. The silence is not peace. The silence is pressure, and pressure eventually speaks. If this deep analysis, the kind that takes the real science seriously and treats you as someone capable of understanding it, is useful to you, take a moment to subscribe and turn on notifications. The next video in this series examines the real-time USGS and PNSN monitoring platforms in detail, walking through the actual dashboards you can access today to watch the Cascadia system in real time. The comment section below is where I want to hear from you. After 3 hours with this data, I have a question I genuinely do not have a confident answer to, and I want to know what you think. The 2026 TIER discovery has added complexity to the Cascadia hazard picture. One interpretation is that the complexity reduces the probability of a full 9-magnitude zone-wide rupture. Another interpretation is that the complexity makes any rupture scenario harder to predict and therefore harder to prepare for. A third interpretation is that the TIER is simply another data point in a data set that has been pointing in the same direction for 40 years. The fault is loaded, the lock zone is full, and the question of when has been answered by the geological record as within the current interval. Which of those interpretations do you find most compelling? Not the most frightening, not the most reassuring, the most accurate. That conversation in the comments below is the most valuable thing that can come out of 3 hours of your time with this data. The fault has been silent for 326 years. The silence will end. The only question that matters now is what we do before it does.